Voyager 1 just reached a region. No human machine was designed to survive. What's actually true, what's exaggerated, and what's happening to humanity's farthest spacecraft? Right now, Voyager 1 is currently about 8 billion miles from Earth, moving through interstellar space, still transmitting, and still, after 49 years of continuous flight, doing something no other human-built object has ever done. That's the direct, verified core of this story. It is not, however, a story about a single moment when the spacecraft crossed into some newly hostile zone it was never meant to enter. It's a longer, stranger, and in some ways more impressive story about a machine engineered in the 1970s for a 4-year planetary flyby that has instead spent nearly 5 decades pushing further into conditions its designers never fully anticipated, and that continues to survive there today through a combination of original engineering and constant, deliberate management from a shrinking ground team back on Earth. Start with what no human machine was designed to survive actually refers to, because the honest answer is more specific and more interesting than the phrase alone suggests. Voyager 1 and its twin, Voyager 2, are the only 2 spacecraft ever built that currently operate beyond the heliosphere, the enormous bubble of solar wind and magnetic field that the sun projects out into space, forming a kind of boundary around the entire solar system. Voyager 1 crossed that boundary, known as the heliopause, on August 25th, 2012, at a distance of about 121, 6 astronomical units from the Sun, roughly 4 times farther out than Neptune's orbit, becoming the first human-made object in history to leave the heliosphere and begin operating in true interstellar space. The crossing is the real version of the region no human machine was designed to survive, framing. Voyager wasn't built for interstellar space. It was built originally to fly past Jupiter and Saturn and send back pictures and data during a mission expected to last around 4 years. Everything that happened after that, including the entire, nearly 5-decade stretch that followed, has been an extended, improvised second act. The crossing itself, when it actually happened, turned out to be far messier and more scientifically contentious than most people assume. The textbook prediction for what a spacecraft should experience at the heliopause was straightforward. The sun's magnetic field, spun into a spiral shape by the sun's own rotation, should give way abruptly to the separate magnetic field of interstellar space, which points in a different direction entirely. A spacecraft crossing the boundary should feel that field swing sharply to a new heading, and that swing was expected to be the clearest, most unambiguous sign of the crossing. That's not what happened. Voyager 1's magnetometer recorded the strength of the surrounding magnetic field increasing, as expected, but its direction barely changed at all, remaining stubbornly aligned with the sun's own spiral field even after the spacecraft was, by every other measure, outside the heliosphere entirely. 2 of the spacecraft's remaining instruments were telling 2 different stories at once. Its particle detectors said Voyager 1 had already crossed into interstellar space. Its magnetometer said the boundary hadn't behaved the way physics predicted it should. What resolved the disagreement wasn't the magnetic field data at all, but the spacecraft's particle counters, which recorded a genuinely dramatic shift. The flow of lower energy particles produced inside the heliosphere by the sun's own solar wind dropped away to almost nothing, while the flux of high-energy galactic cosmic rays, particles that originate far outside the solar system entirely, surged upward and then stayed at that elevated level. That combination, low-energy solar particles vanishing while high-energy galactic particles spiked, was the clearest possible signature that Voyager 1 and why had left the sun's direct influence behind, even though the magnetic field itself hadn't rotated the way older models predicted. There should have been an additional independent way to confirm all of this using the spacecraft's plasma science instrument, which could have measured the density of charged particles around the spacecraft directly and settled the question immediately. That instrument, unfortunately, had already stopped working back in 1980, more than 3 decades before the crossing actually happened, which meant the science team had to rely entirely on indirect evidence rather than a single definitive reading. The eventual answer came almost by accident. In April 2013, a burst of solar activity sent a pressure wave rippling outward through the solar system, and when it reached Voyager 1's location, it set the surrounding plasma vibrating in a way the spacecraft's remaining instruments could actually detect and measure. From those vibrations, scientists were able to calculate the density of the plasma around the spacecraft directly, and the number came back matching the expected density of true interstellar space almost exactly, far too dense to be explained by anything still connected to the sun's own bubble. Working backward from that data point, the science team was able to fix the actual crossing date at August 25th, 2012, even though the confirming measurement didn't arrive until 8 months later. NASA didn't publicly announce the achievement until September 12, 2013, more than a year after the crossing itself had actually occurred. specifically because of how much internal disagreement and cross-checking the ambiguous magnetic field data had required before the team felt confident enough to say, officially, that Voyager 1 had left the solar system's direct influence behind for good. The picture that emerged from all of this wasn't the clean, single-line boundary that popular science had long imagined. In the months leading up to the actual crossing, Voyager 1 had already passed through a strange transitional zone that the mission team nicknamed the Magnetic Highway, a region where the sun's magnetic field lines and the interstellar magnetic field appeared to connect directly with each other, allowing particles to leak back and forth across what should have been a sharp dividing line. Rather than a wall, the heliopause turned out to be layered and porous, a soft, blurred boundary rather than a hard edge, which is part of why the magnetic field itself never delivered the clean, directional swing scientists had originally expected to see. A second, independent confirmation of all of this arrived 6 years later, when Voyager 2, Voyager 1's twin spacecraft, launched around the same time but sent on a different trajectory through the outer solar system, crossed its own heliopause boundary on November 5th, 2018, at a slightly different distance of about 119 astronomical units, and in a different direction across the sky entirely. Crucially, Voyager 2's plasma instrument, unlike its twins, was still working at the time of its own crossing, which meant scientists finally got the direct, unambiguous plasma density measurement that Voyager 1 had never been able to provide. Voyager 2 recorded exactly the kind of sharp jump in particle density that theory had always predicted, along with plasma temperatures between 30,000 and 50,000 Kelvin, far hotter than the surrounding interstellar medium, almost certainly the result of solar wind plasma being compressed as it collided with the boundary. And just like its twin 6 years earlier, Voyager 2's magnetic field also failed to rotate the way the old textbook model predicted, which confirmed that Voyager 1's earlier, messier result hadn't been some kind of fluke or instrument malfunction. Two spacecraft, launched decades ago, crossing the same fundamental boundary years apart and in different parts of the sky, had independently returned the same unexpected answer about how the edge of the solar system actually works. None of this happened in isolation from the spacecraft's own physical condition, and this is really where the design to survive framing becomes genuinely accurate rather than just dramatic. Voyager 1 launched from Cape Canaveral in 1977, carrying 11 separate scientific instruments and 3 radioisotope thermoelectric generators, power sources that convert the heat produced by the natural radioactive decay of plutonium-238 directly into electricity, rather than relying on solar panels, which would have been useless once the spacecraft traveled far enough from the sun. At launch, those 3 generators together produced roughly 470 watts of usable power. That output has been declining steadily ever since by a consistent rate of roughly 4 watts per year, as the plutonium fuel source naturally decays and the hardware itself slowly ages, and current output has fallen to somewhere around 250 watts, roughly half of what the spacecraft started with nearly 5 decades ago. That steady, irreversible power decline is the actual mechanism driving everything that's happened to the mission over the past 25 years, and it's the real reason the spacecraft's survival has never been passive. Engineers at NASA's Jet Propulsion Laboratory have been progressively and deliberately shutting down individual instruments, heaters, and other onboard systems since the late 1990s, specifically to keep total power consumption below the shrinking supply the generators can still provide. Of the original 11 scientific instruments Voyager 1 launched with, only a small handful are still functioning today. The cosmic ray subsystem, one of the instruments that had helped confirm the 2012 heliopause crossing in the first place, was itself switched off in February 2025. The low-energy charged particle instrument followed in April 2026. By that point, NASA's own status listings showed only 2 Voyager 1 science instruments still actively returning data: the magnetometer, the same instrument whose confusing directional readings had complicated the 2012 crossing analysis, and the plasma wave subsystem, which had been essential in helping confirm that same crossing after the primary plasma instrument had already failed decades earlier. Every one of these shutdown decisions involves a genuine trade-off that the ground team has to weigh carefully, since turning off a heater or an instrument saves a small amount of power now but permanently ends whatever data or function that hardware provided, with no possibility of ever turning it back on once its associated heater has gone cold enough in the extreme temperatures of deep space. Based on current JPL estimates, the mission is expected to continue functioning in some reduced form into the early 2030s, at which point the remaining power supply is projected to finally drop below the minimum threshold needed to operate any instrument at all, effectively ending the spacecraft's ability to return scientific data even if its basic systems technically continue running a while longer after that. Set against that backdrop, the next major milestone the mission is approaching is less about danger and more about sheer scale, though it's arguably the most tangible. easy to understand marker of just how far Voyager 1 has actually traveled. Sometime around mid-November 2026, current NASA tracking places the date at November 15th, 2026, and separate reporting has cited November 18th, 2026 at 2:16:07 a.m. Pacific time as the precise moment. Voyager 1 will cross what's known as the 1 light day distance from Earth, becoming the first human-made object ever to do so. A light day is exactly what it sounds like. The distance light itself travels through a vacuum in 24 hours, which works out to roughly 16. 1 billion miles, or about 9 billion kilometers. Once Voyager 1 passes that threshold, any radio command sent from Earth will take a full 24 hours just to reach the spacecraft, and if it's able to respond at all, that response will take another full day to make the return trip back to Earth. Susie Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, has described the practical reality of that communication delay in strikingly simple terms. If her team sends a command and says, "Good morning" to Voyager 1 at 8 in the morning on a Monday, the spacecraft's response won't actually arrive back on Earth until roughly 8 in the morning on Wednesday, 2 full days later, once the light day threshold has been crossed. It's worth being precise about what this milestone does and doesn't represent, because it's easy to misread as some kind of dramatic boundary crossing in its own right. Unlike the 2012 heliopause crossing, the 1 light day mark isn't a physical boundary or a scientific threshold at all. It doesn't mark Voyager 1 leaving anything or entering anything new in a physical sense. It's purely a measure of distance and communication delay, a human way of grasping just how enormous the gap between Earth and the spacecraft has actually become, expressed in terms of how long a conversation with it now takes, rather than in raw miles or kilometers that are difficult to intuitively picture. That distinction matters because the light day milestone and the heliopause crossing often get blurred together in casual coverage, when they're really two entirely different kinds of events. The heliopause crossing in 2012 was a genuine physical transition, the moment Voyager 1 actually left the Sun's direct sphere of influence and entered a fundamentally different physical environment, one dominated by interstellar plasma, interstellar magnetic fields, and a significantly higher, near-constant flux of galactic cosmic radiation that the heliosphere had previously helped shield the inner solar system from. The upcoming light day milestone, by contrast, is simply a distance marker along a journey that's been continuous and gradual ever since that 2012 crossing happened. Voyager 1 didn't suddenly encounter a new hostile environment in 2026. It's been living in that environment for 14 years already, and continues moving steadily deeper into it every single day, at a current velocity of roughly 17 kilometers per second relative to the Sun. It's also worth being clear about what the spacecraft is and isn't still capable of scientifically, since that's ultimately the reason continued operation matters at all beyond simple engineering achievement. Even with only 2 working instruments left, Voyager 1 retains real scientific value specifically because no other spacecraft currently operating anywhere is positioned to take direct, in-place measurements of interstellar space the way it can. Ground-based and near-Earth instruments can observe cosmic rays and interstellar phenomena indirectly, filtered through the heliosphere's own effects. But Voyager 1 sits physically outside that filter, providing scientists with genuine unfiltered measurements of the local interstellar medium that quite literally cannot be obtained any other way, from any other location, using any other currently existing hardware. Data from Voyager 1's still-functioning magnetometer and plasma wave subsystem continues to feed directly into ongoing research on galactic cosmic ray spectra, interstellar magnetic field structure, and the broader physics of how stars like the Sun interact with the surrounding galaxy, research that in some cases is still actively being published in peer-reviewed journals using data the spacecraft is providing in something close to real time. Both Voyager spacecraft have also proven unexpectedly useful for tracking large-scale disturbances that ripple outward from the Sun and propagate all the way out through the heliosphere and into interstellar space itself. In one documented case, a large pressure disturbance detected first by Voyager 2 back in mid-2012 was later observed rippling past Voyager 1's own location 93 days after Voyager 1's heliopause crossing, producing a strikingly similar, clearly related dip in galactic cosmic ray readings at both spacecraft, recorded from 2 different points in space, separated by a measurable time lag. That kind of 2-point deep space measurement of a single physical event propagating outward from the Sun simply isn't possible with any other currently operating spacecraft, which is a significant part of why mission planners have continued fighting to keep both Voyagers alive and returning at least some data for as long as physically possible, even as instrument after instrument has had to be permanently switched off. None of this changes the fundamental underlying reality driving the whole story, which is that Voyager 1's power supply is declining in a way nothing on Earth can fix or reverse. It cannot be repaired, refueled, or upgraded from a distance of over 15 billion miles. And it will continue losing roughly 4 watts of usable power every single year for as long as it continues operating at all. Following the same fixed physical decay curve, its plutonium-238 fuel source has followed since the moment it launched in 1977. The mission team's entire operating strategy at this point isn't really about extending the spacecraft's life in any open-ended sense, since that ultimate endpoint is fixed by basic nuclear physics and can't be negotiated with. It's about carefully, deliberately sequencing exactly which capabilities get shut off and in what order, trying to preserve the specific combination of instruments and functions that will keep the spacecraft scientifically useful and able to communicate with Earth for as long as that's physically possible, given a power budget that only ever moves in one direction. There's a reasonable, well-supported chance the spacecraft manages to keep transmitting at least basic engineering data through 2027, which would mark 50 full years of continuous operation since its 1977 launch, an anniversary the mission team has explicitly said they're actively working toward. Beyond that point, current projections suggest Voyager 1 will likely continue operating in an increasingly limited, stripped-down form into the early 2030s, before its power supply finally drops below the minimum threshold required to run any of its remaining instruments or transmit any further data back to Earth at all. When that final threshold is eventually crossed, Voyager 1 won't stop existing or stop moving. It will simply go silent, continuing to drift outward through interstellar space indefinitely, carrying its golden record and its now permanently unreadable final instrument readings with it long after the last usable watt of power has finally run out. To understand how a spacecraft ends up in this position at all, it helps to go back to where the mission actually started, because Voyager 1's current situation only makes sense in light of a very specific and unusually lucky piece of orbital timing. In the 1970s, mission planners at NASA's Jet Propulsion Laboratory realized that Jupiter, Saturn, Uranus, and Neptune were about to align in a configuration that only occurs roughly once every 175 years, one that would allow a single spacecraft, using a series of gravity assist maneuvers, to visit all 4 outer planets in sequence using a fraction of the fuel that would otherwise be required, letting each planet's own gravity fling the spacecraft onward toward the next with increased velocity, rather than needing onboard propulsion to make the entire journey alone. 2 nearly identical spacecraft were built to take advantage of that alignment. Voyager 2 launched first on August 20th, 1977, followed 16 days later by Voyager 1, which lifted off from Cape Canaveral on September 5th, 1977, aboard a Titan 30E Centaur rocket. Despite launching second, Voyager 1 was placed on a faster, more direct trajectory, and it overtook its twin on December 15th, 1977, going on to reach Jupiter first. Voyager 1 made its closest approach to Jupiter on March 5th, 1979, and during that encounter alone, returned roughly 19,000 photographs of the planet and its largest moons. That single flyby produced a string of genuine scientific firsts: the discovery of a thin, previously unknown ring encircling Jupiter, the identification of 2 new Jovian moons named Thebe and Metis, unprecedented close-up imagery of the Great Red Spot, and, most significantly, the first direct observation of active volcanic activity anywhere in the solar system beyond Earth itself, discovered on Jupiter's moon, Io. From Jupiter, Voyager 1 used the planet's gravity to slingshot onward toward Saturn, arriving for its closest approach on November 12, 1980. Mission planners deliberately routed the spacecraft for a close flyby of Titan, Saturn's largest moon, and, at the time, the only moon in the solar system known to have a substantial atmosphere of its own, a scientific priority significant enough that it permanently determined the rest of Voyager 1's trajectory. That Titan flyby bent the spacecraft's path sharply upward, out of the flat plane in which the planets orbit the Sun, which meant Voyager 1 would never be able to visit Uranus or Neptune afterward, unlike Voyager 2, which continued on to fly past both of those planets later in the decade. At Saturn, Voyager 1 discovered 5 previously unknown moons, along with a new ring, subsequently named the G ring, adding to an already substantial list of firsts credited to the mission. With its planetary encounters complete, Voyager 1's scientific mission, as originally designed, was technically finished. It would never visit another world. For nearly a decade afterward, the spacecraft simply coasted outward through comparatively quiet space, still transmitting engineering and particle data, but with no more planets left to encounter. Then, on February 14, 1990, at the specific urging of Voyager imaging team member and astronomer Carl Sagan, and over the practical objections of engineers concerned about pointing the spacecraft's camera anywhere near the direction of the Sun, ground controllers turned Voyager 1 around and had it look back toward the solar system one final time. From a distance of roughly 7 billion miles, at 40 astronomical units from the Sun, The spacecraft captured a mosaic of 60 images showing 6 of the solar system's planets in a single sweeping view: Neptune, Uranus, Saturn, Jupiter, Venus, and Earth. Mercury was too close to the sun's glare to appear, Mars was too dark to register clearly, and Pluto, still classified as a planet at the time, was simply too small and dim to be visible at all. In that mosaic, Earth appeared as a single point of light smaller than 1 pixel across, caught in a scattered band of sunlight. Sagan later named the image the pale blue dot, and it went on to become one of the most widely reproduced photographs in the history of space exploration, eventually lending its name to Sagan's own 1994 book on humanity's place in the cosmos. Roughly 34 minutes after that final shutter closed, Voyager 1's cameras were switched off permanently, a deliberate decision made specifically to conserve power for the decades of Operation mission planners hoped still lay ahead. Those 1990 images remain, to this day, the last photographs either Voyager spacecraft has ever returned to Earth. From that point forward, Voyager 1's mission formally shifted into what NASA designated the Voyager Interstellar mission, beginning January 1st, 1990, with an explicit new objective: to extend the spacecraft's exploration beyond the outer planets entirely, toward the outer limits of the sun's influence and, if the hardware held out long enough, into interstellar space itself. That reframing turned out to be remarkably prescient. Everything covered earlier in this piece, the 2012 heliopause crossing, the ongoing instrument shutdowns driven by declining plutonium power, and the upcoming 2026 light day distance milestone, is really just the continuation of that 1990 decision to keep the mission going for as long as physically possible, long after its original planetary objectives had already been fully achieved. It's also worth noting that the spacecraft's engineering has occasionally surprised even the people who built it. Its trajectory correction maneuver thrusters, small onboard rockets originally used to fine-tune the spacecraft's path during its planetary flybys, hadn't actually been fired since November 1980 during the Saturn encounter. Decades later, as the primary attitude control thrusters Voyager 1 had been relying on to orient itself toward Earth began to show signs of degrading performance, engineers made the decision to test whether those long dormant trajectory thrusters could still function after sitting unused for 37 years. The test succeeded, and NASA was able to switch the spacecraft back over to using those older thrusters for orientation control, a move that meaningfully extended how much longer Voyager 1 could reliably keep its antenna pointed at Earth. It's a small technical detail, but it captures something true about the entire mission. Nearly every additional year Voyager 1 has operated beyond its original planned lifespan has come from exactly this kind of resourceful, incremental engineering, squeezing continued function out of hardware that was never expected to still be running this many decades later. Voyager 1 also carries something that has nothing to do with data collection at all, but is worth mentioning because it speaks to how the mission was conceived from the very beginning, as something meant to outlast any practical scientific return. Bolted to the spacecraft's exterior is the Golden Record, a gold-plated phonograph disc containing a curated selection of sounds, music, spoken greetings in dozens of languages, and encoded images meant to represent life and culture on Earth, included on the extremely remote chance the spacecraft is ever encountered by another spacefaring civilization at some point in the almost incomprehensibly distant future. Long after its instruments have gone silent and its power has finally run out entirely, Voyager 1 will continue drifting through interstellar space, carrying that record with it, a physical object that will likely persist far longer than the mission itself, or than any of the engineers who built it. Looking further ahead than any current mission timeline can meaningfully plan for, Voyager 1 is not headed toward any particular star system, and it isn't aimed at one on purpose. It's simply following the trajectory set by its final planetary gravity assist back in 1980, continuing outward in roughly the same general direction indefinitely. In tens of thousands of years, on a timescale that dwarfs the entire span of recorded human history multiple times over, it will pass at a considerable distance from other stars in the galaxy, not as a planned encounter, but purely as a consequence of the vast, mostly empty space. It will continue crossing, regardless of whether its instruments or transmitters are still working by then. Long before any of that happens, Voyager 1 will have already gone silent, its final transmission back to Earth having occurred sometime in the early 2030s by current estimates, after which it becomes, in every practical sense, an inert object rather than an active mission, still moving, still carrying its golden record, but no longer capable of telling anyone on Earth anything about where it is or what it's encountering. It's worth placing all of this in context against other similar deep space missions, because Voyager 1's continued operation this far past its original design life is not the norm, it's a genuine outlier. NASA's earlier Pioneer 10 and Pioneer 11 probes, launched a few years before the Voyagers, and sent on broadly similar outward trajectories, Both went silent decades ago. Their far smaller power sources and simpler onboard systems, unable to match the kind of extended, carefully managed operational life engineers have coaxed out of the Voyager spacecraft. Even within NASA's own more recent deep space missions, few have approached anything like the same combination of distance, duration, and continued scientific output. That comparison isn't meant to diminish other missions, most of which were designed with entirely different objectives and operating lifespans in mind from the start. But it does help explain why Voyager 1 in particular has become the specific benchmark against which almost every subsequent conversation about long-duration spaceflight and deep space communication gets measured, including recent milestones set by newer missions like New Horizons, which itself has drawn direct comparisons to the Voyagers as it continues operating billions of miles past Pluto. There's also a human dimension to this story that's easy to overlook amid the engineering and orbital mechanics, and it's worth stating plainly. The scientists and engineers who originally designed, built, and launched Voyager 1 in the 1970s largely could not have anticipated that the mission would still be actively managed, still generating peer-reviewed scientific findings, and still making genuine headlines nearly 50 years later. Many of the engineers currently responsible for keeping the spacecraft operational, making the specific decisions about which heater or instrument to switch off next in order to preserve just a little more usable power, were not yet born when Voyager 1 first launched. The mission has effectively outlived not just its own original design specifications, but multiple generations of the people who work on it, handed down as an ongoing engineering and scientific responsibility from one team to the next, each managing the same steadily declining power budget their predecessors were managing years before them. To bring this back to the direct, exact point, is Voyager 1 currently in a region no human machine was designed to survive? In the narrow, technically accurate sense, yes. It was engineered for a several-year planetary flyby mission, not for permanent operation in interstellar space, and it has nonetheless been operating in exactly that environment, continuously, for 14 years and counting, a region defined by significantly elevated cosmic radiation, an environment its original 1970s era instruments were never specifically built or tested for. But there was no single dramatic moment when it suddenly entered a kill zone it might not survive, and there's no urgent new crisis unfolding right now. What's actually happening is slower, quieter, and in its own way more remarkable. A machine built half a century ago, using electronics far less capable than what sits in an ordinary calculator today, continuing to function, adapt, and return genuinely useful scientific data from a region of space no other human-built object has ever operated in, managed the entire time by a shrinking team of engineers on Earth making careful, irreversible decisions about exactly which parts of a dying spacecraft to keep alive, and for how much longer.